Okay, welcome back everybody. We're talking about hypothesis testing. There's lots of warnings about this. I just want to point out and I think you guys already get the idea, I don't love this because there are issues. In addressing those issues, to do it thoroughly, you have to consider things like how far from the null would you really need to be before you're willing to reject it. And that should have context depending on the problem that you're working on. And that's not the way the field has decided to go. They've tried to auto-procedure this. I want to point out, one of my friends said to me in my first year of graduate school, Neyman-Pearson sent back statistics 200 years. And I thought to myself, well, statistics hasn't even really been around for 200 years, so how could that be? And I don't really even understand what Neyman and Pearson are saying, but it is that if P ducks alpha, you reject sort of thing. But I want to point out, Neyman and Pearson didn't do that. They didn't tell you that if P ducks alpha, you should just reject. They also told you a lot of other things. You should look at the full power curve, and you should calibrate what your meaningful effect size would have to be before you're willing to reject the null. Both Neyman and Pearson, and this is baby Pearson, this is Egon Pearson, Carl Pearson's son. He believed he was patching up an issue with Fisher's claims about null hypothesis testing. And so he was presenting this from a purely mathematical perspective and saying, if you want to do what you're doing, I'll try to give you a mathematical argument for doing it. And I guess Fisher didn't like that. So I would say Fisher is wrong and Neyman and Pearson are correct in terms of their mathematical formulation of everything. But I think Neyman and Pearson also would agree that on its own, without talking about the effect size and calibrating that, this is all very meaningless. Saying that, a lot of people saw what they were doing and realized you could just shortcut this and just calibrate the type 1 error, check if P ducks alpha, find a test so that P does duck alpha, and lo and behold, you're in the game, and they didn't calibrate the effect size. So, Bill Woodall was talking about this in his presentation a couple weeks ago, that you basically need to calibrate thresholds for what meaningful effect size would be, but he didn't tell us how to do it. So he just said, I don't know, what you want to do is collect enough samples so that you drive down the variability so that that variability is well within the thresholds that you set. And so I agree with that, but how do you set those thresholds in a real problem? And I usually say the context matters. So in problems like this, right here, this example, this is the typical example that we give Stat 101 students over and over and over and over again. And it gets a little bit worse with the sharp test. And we tell them, why don't you compute the test statistic, compute the p-value from that, and at an alpha level of 0.05, make a decision. And so they're turning you into a robot when you do that. I'm going to try to argue against that. I would say, in this case right here, the one-sided thing, things don't go horribly wrong. It's in the sharp test that things go horribly wrong.
I think you made a calculator.
Where?
H alpha is just alpha. I'm sorry, theta. Not theta, sorry, theta. Just all of theta. You're saying the same thing.
Oh, yeah. I got it. This one. Yeah. That one.
Again.
Did I do it again?
Yeah. Molecular duration test gave motherboard. Motherboard. X1. Yes, the one below it. Change this.
Oh, yeah. So, I do it too. And at 9 a.m. bounds confuse me, And so, that's usually why I write all the bounds on the board when I walk in, so I know which direction we're going. But I think it's all right now. So, I want to point out in this test right here, if somebody showed this to me, I'd be okay with the typical thing that people do. If I did a Bayesian calculation, I would come up with whatever. Their p-value would be my posterior distribution. I'll try to explain that later on. For the sharp test, I could never come up with, you can't come up with that correspondence. And I'll try to explain that as well. But if somebody did show me a test like that and they're trying to hypothesize about theta, and theta is a one-dimensional thing, I say just estimate it. Estimate it, tell us where you think it could be, however you interpret that, but tell us valid ranges for theta, and just do that. What I really wish people would do is just write down the likelihood function. It shows where the likelihood function is, and theta should be in the massey part of it. Exactly how you define that and what you're using as your objective function, probably a little bit more needs to be discussed there to calibrate it. A Bayesian has a way of doing it. They multiply by a prior, and then they look at posterior probabilities that are large. And you can threshold what large is. Something equivalent happens here for the Neyman-Pearson thing, but their interpretation isn't about a posterior probability. But it does turn out to be equivalent if you use the typical prior people would use on theta. But in any case, I wouldn't test. I would just say, here's what I think theta is. You make your decisions based off of that. And that's what I wish people would do. I do get it that if we move to high-dimensional spaces, at some point you're going to need to simplify the problem. Probably take some coefficients and make them 0, but you still need to be aware of all the issues in hypothesis testing to analyze whether or not your model selection procedure is working well. So I'm sympathetic to people wanting to answer this question, but I'm not sympathetic about doing it in a one-dimensional setting. So because you could draw everything and show us where you think theta is, and it's bounded all very nicely. So I think only in high-E settings should you even be doing this in the first place. So hopefully when you guys teach Stat 101 or something like that, and you're teaching hypothesis testing and the book tells you turn your students into robots, you say, not so fast, you need to calibrate the effect size for any of this to be meaningful. And I'll say a little bit more about that. Do what Neyman and Pearson actually told us to do. Wald came in and he kind of, took it a step further, and he kind of told us what we should do with everything. But saying that, Neyman and Pearson never did the thing where P ducks alpha, you reject. They would never do it, but now somehow we've accepted we should do that, and I think it has to do with our Stat 101 upbringings. So hopefully we can break us of that. So my intention is not to teach you exactly what to do, but to teach you the issues in this. And at the end of the day, you're going to have to make your own decisions. Okay, here's one way of doing this sort of thing. So here's an example that we were covering last time. You might base your decisions off of the likelihood ratio test. So you might look at the ratio of likelihoods, where this is going to be the max over theta in the null set likelihood. And this will be the max over theta likelihood. So comparing these two likelihoods, I think that does make sense. So in looking at the best model in that model class kind of makes some sense. So we've computed that thing, and what you could say is that if this thing is small, then basically the support of the numerator, the support in the null space, is really small compared to everything else. And so you would be inclined to reject that. It's less plausible, it's less likely. And so we threshold that by some number C. So this is my likelihood ratio right here. I bound that by C. C lives between 0 and 1 because of the way they set all this up. The denominator is normalized over both the null and the alternative space. You can simplify all of this. So this is the exact same C, and here's an equivalent condition right here. So I flip the sign, the inequality, because I have that negative sign floating around, and it was this negative sign. So we simplified everything, and this is our rejection criteria. If you were doing the max likelihood ratio test, this would be the thing that you would compute, and that's equivalent to some statement on x1. And I think I wrote this out just a little bit differently last time, and I said reject if x1 is bigger than this, right here. I just want to point out that this first part is just some other number. And I'll add theta naught from it. And so all this is saying is if x1 is very far from theta naught, you should reject it. And that's all this statement says. So if x1, the min order statistic, is far from theta naught, then we'll reject it. Of course, the question is, what's far mean? And how do you think about that? And Neyman and Pearson are going to tell us we should calibrate that using a probability statement, and we can compute the probability of the min order statistic. So power functions are based off of this. So our power function for this problem would be the probability that x1 is greater than some constant, and I'm just going to write it in as k, some other constant, because that thing right there is a constant. You give me c, you give me n, this is just some other constant. C lives between 0 and 1. Where does this constant right here live, if it's going to be the same thing? So this is k. I'll give you one of the endpoints, 0. Infinity. So this thing just lives between 0 and infinity. Plus theta naught. And so what you would have to do to compute this power function is you would have to write down the probability distribution for x1, or you can write down the probability density for x1 and then integrate over it. And you can compute what that probability is. You're going to calibrate your test to type 1 error rate through this value. So this is going to calibrate the test. And what we're going to do with this calibration, I'll show you some examples of this. We don't actually, for this, I don't think anybody knows off the top of their head what the various quantiles are for this distribution. So I'll try to write down the distribution that we're all familiar with, and we could understand how to choose k. But we're going to calibrate the test to have some fixed maximum type 1 error rate. And so we're testing in 2 different regions, and I can test in this region right here. This is the region. This is, probably need to give you an example instead of just saying a bunch of words about this. But I'll just recap and say that's going to calibrate the max type 1 error rate. I can pick that value, and then I can look at the probability of rejecting in the alternative space as well. So I don't want to do that whole calculation. It's imaginable. You could do it. You could work it all out. I don't want to go through the whole order statistic thing, but that's why we've covered order statistics in the first place, because they turn out to be min-sufficient statistics for a lot of problems that involve boundary conditions. But that's the name of the game of about what you would do. Let me show you another example. Let me show you this example first. This is the one that probably you may have seen in the Stat 101 S class, and I wish you would see this example for longer and talk about all of the issues. Let's just work through it and see that this is something that you might already know. So all these tests that we've been using are based off of the likelihood ratio test. So all the stuff they teach you in Stat 101 are based off of this test that we're studying. So let's look at this example. x1, xi is normal, theta, sigma squared. I'm going to say that's known. If it weren't known, you would need to do something with it. Integrate it out, substitute an estimate for it. Bayesians and non-Bayesians will do the same thing. And they'll probably estimate that using some form of S squared. So we'll just let it be known. We'll say we've got n data points, everything is II. So typical problem. And I want to test this hypothesis right here. So let's compute the likelihood ratio test statistic. By the way, this is also what Bass was referring to is the null hypothesis significance testing procedure. So Neyman-Pearson likelihood ratio test, if likelihood ratio test ducks a constant. So, okay. So the likelihood ratio test for this, lambda x, is going to be equal to max theta in the null space. And I'm going to divide by the max over all of theta. And of course, I'm taking maximums over the likelihood function. Likelihood function just looks like this thing. Proportional to I goes from 1 to n, 1 over 2 pi, sigma e to the minus 1/2 xi minus theta. And I could work with this form if I wanted to, but I know enough at this point to know I don't like this product. I would like to simplify all of this. And I can simplify everything using the minimal sufficient statistic. So it not only saves computation time, save RAM in your computations, but it also simplifies mathematics. So lots of good reasons to use minimal sufficient statistics. So what is the min sufficient statistic for theta? X bar. So good. X bar is min sufficient. We can do that at 9 a.m. So I'm going to rewrite the likelihood using X bar. And this is going to be proportional to 1 over root 2 pi sigma over root n e to the minus 1/2 x bar minus theta squared sigma squared over n. And you can verify that these are proportional. Of course, if we didn't know sigma and we did that, we've just made a huge mistake. So because the sum of the xi's minus x bar squared, that's what's sufficient for sigma squared. And that doesn't appear in this equation. So if you expand all of that, you'll see that that term factorizes out, and we just get rid of it. So that's the form that we're going to use. It'll make everything just a little bit simpler. If we did use this form, there's just more algebra to do. So we'd get equivalent answers. So question is what is the maximum likelihood ratio in the null set? Let's do the denominator first. What's the maximum of this likelihood function right here when it's unconstrained? What's the maximum likelihood estimate? It's hard. So I'll plug in my 1 over root 2 pi sigma e to the minus 1/2 x bar minus x bar squared over sigma squared. Okay. So also we have to be careful what we're testing right here. Theta is greater than theta naught, and so I probably need to consider various theta naughts in all of this. Let's say theta naught was over here. Here's x bar. So where's the maximum? So we're going to do the max over the null set. And if I've said theta naught is over to the left of x bar, what's the maximum? Theta naught. It occurs at theta naught. So right there, because this is increasing. If theta naught were over here, it's x bar. So the likelihood ratio test would be 1. The likelihood ratio test stat would be 1 if theta naught were greater than x bar, and you wouldn't be inclined to reject that. So that's not going to define your rejection region. It's when theta naught is less than x bar that we're going to see some mathematical parametric form that's going to define our rejection region for us. And so that's the one that I'm going to write down for theta naught greater than x bar. The likelihood ratio test stat is 1. You're not going to reject that. Nobody would reject it. So e to the minus 1/2 x bar minus theta naught is what we come up with right there. This is squared. I've got a sigma squared divided by n, and before somebody corrects me, I'll just throw that n down there. So this is just this. Oh, there's a sigma in here, there's a root n in there, and there's a root n in there. I'm being really cavalier about this because I already know all the normalizing constant jump cancels, and so already in my mind I'm always thinking, I don't need to worry about it. So I would have tossed it instantly, but you'll notice once again, using likelihoods, every time you use a likelihood, you use it in ratio form. So if you use it in additive form, it's because you're using log likelihoods. So I want to point out Jack Good, one of our old colleagues here at Virginia Tech, talked about, I forget what he called it now. He's trying to recall something. I'll have to remember, but he talked about everything on log likelihood scales. He had something similar to this, and he called it the information. So another one of these information things. I forget exactly what he called it. But same thing, he said, oh, it makes a lot more sense because it's additive and things should be additive. But I don't know if I agree with that. It's exactly the same thing as this. So those cancel right there. This thing right here is 1. So that's kind of convenient. So this is going to look like e to the minus 1/2 x bar minus theta naught squared over sigma squared over n. And what we're going to do is we're going to bound this by some number c. Same thing that we did before. C is going to live in some range. I'll just rewrite all this. This is e to the minus 1/2 x bar minus theta naught squared sigma squared over n, and we want to bound this by c. So we'll just do a little bit of arithmetic and untangle all of this stuff. So this is equivalent to looking at, I'll take the log of both sides, so log of c. I'm going to also multiply by my minus 1/2 in all of this, so minus 1/2. So I took the log, I multiplied both sides by about minus 1/2, and when I do that, I flip the inequality. So x bar minus theta naught over sigma over root n, and I'll take the square root over here. So this used to be squared in the exponent, and I just square rooted all of it.
Yeah.
You need to take the reciprocal of the 1/2.
Yeah.
Ah, yeah, okay, cool. Another thing that doesn't exactly matter, but you're right. So things that I know won't matter, but you're right. Yeah, that's a mistake. So that's our rejection criteria. So what does this say? If x bar is bigger than theta naught relative to the standard error, then we reject. And we're familiar with this criterion. So we've used that criterion a lot. And so the Neyman-Pearsonian thing says just calibrate to the standard error and that's good enough. Bayesian would say that's not good enough. You need to actually build in a real effect size that's meaningful to you. We'll walk through a calculation like that on Friday or next week. I want to just point out this is another constant. So I'm going to call that k. So c lived between 0 and 1. Where does k live between? 0 and infinity again. So this thing blows up on you. So this is just another constant. So I'm just going to re-encode that as another constant. So what we're looking for is this thing being bigger than some threshold, some constant. And that's what we're going to look at. So the power function is going to be the probability that x bar minus theta naught over sigma over root n is going to be greater or equal to some constant. And that's the thing that we're computing. And you're probably familiar with this. If you took a Stat 101 class, you probably did this all the time. And you were able to figure out your p-value from this calculation. So what's the test statistic that we're looking at? The test statistic that they ask you to compute in Stat 101 is this standardized form based off of our minimal sufficient statistic x bar. And usually there's a lot of statements surrounding that. We've just derived it. So it's all Neyman-Pearson in disguise. Let me come back over here. Let's start thinking about this function. Let me ask you a question. How's that random variable? It's the thing on the left-hand side of the inequality. How is that distributed? So this is a test stat. How is that distributed? It's normal. Which normal? Yeah, maybe. So I agree with you that it's normal, and I agree that the variance is 1. But I don't agree that it's centered at 0. So it's centered at 0 if x bar was generated from the null hypothesis. So with theta naught. So if theta naught was the true generating value, this is normal 0, 1. But we don't know that. So we're testing something like that. We're actually testing the boundary of that condition. And so what we really want to look at is what happens when I condition on the null hypothesis. That's what we'll do. So let's just rewrite this out, power function. Call it b theta. It's a function of theta. I don't actually have my thetas in there. So what is theta? That's either going to live in the null hypothesis range or in the alternative range. But I'm going to say theta is our true value. And so our probability, I'm just going to take x bar, I'm just going to rewrite this, minus theta over sigma squared, sigma over root n, is going to be greater or equal to k plus theta naught minus theta sigma over root n. So all I've done to this equation is I've added theta naught over here, and then I subtracted off theta from both sides. So this is exactly the same thing. So I haven't changed anything. This is equivalent to x bar minus theta naught over sigma over root n is greater than k. Some number. So exact same things. Take theta naught divided by this thing, of course, add it to both sides. That's this one right here. Subtract off theta divided by the standard error on both sides. That's this one over here. So those are equivalent statements. So we're assuming that theta is the true generating value. And we're looking at the probability under different possible generating values of this. So now I've got my theta. This thing was conditioned on theta, the truth, in the first place. So I probably should have written down so you could see the thetas given theta, where that's the truth. And then I know what x bar is generated as if theta were the truth. X bar has mean theta. So that's the notation right here. This is our power function. So let's look at it. So d theta. We can kind of see real quickly that, let's just take a limit. Let's say theta goes to negative infinity. So if theta goes to negative infinity, I'm subtracting off negative infinity over on the right-hand side. So this is plus infinity, if you're okay with that terminology. I understand, I just really pissed off my mathematics teachers. So, limit. So that's going to be some big number over here. It'll dominate that. That's just some constant that you picked. So this will get really big. What's the probability that this is going to be bigger than something really, really, really big? No matter how big you think of, it's bigger than that. So this goes to what? 0. That's good. So that's in the alternative space right here. So if theta is small values, where I'm capping it by theta naught, then that's the alternative range. So this is for the alternative space. So this is H alpha right here, the alt space. The power is going down to 0. That's a good thing. We don't want to reject when we're in the alternative space. The null is true. So limit theta goes to infinity of our power function. What does that go to? 1. And that's where we're in the other part of the space. We would want to reject. So what does this thing look like right here? It's this curve. It looks like that. And if you want to compute actual probability values to compute this curve, you could do it. But you can probably already inspect this thing and figure out that that curve looks like this, right here. What we're going to do in this is let's imagine theta was theta naught. So that's the boundary in our null space. And so where does that actually happen? I'm going to draw it right here. And so when theta is equal to theta naught, this thing is 0. And this thing is theta naught. When theta is equal to theta naught. And so this is my null space. Yeah, it's that down thing. And so what we can do is we can calibrate this. So the probability of theta minus theta naught over sigma over root n is going to be greater or equal to k. Right there. So when theta is equal to theta naught. So that's this condition. And we're able to get this. So this value k is calibrating the max type 1 error rate. So, which happens right here. So this is the max type 1 error. They get smaller over here. And so what you're doing in the typical Neyman-Pearsonian setup, or using a likelihood ratio test, is that constant that you're using somehow conforms to calibrating the probability of your max type 1 error rate. So when people are talking about the type 1 error rate, they're talking about the maximum in that whole set. What's the maximum error you could incur? So for instance, if k were equal to, I don't know if I know these values off the top of my head, 1.28, then this probability, max type 1 error, is equal to 0.1. If k were equal to 1.645, then our max type 1 error is equal to 0.05. Give you one more value. I do know some of these. 1.96. Of course, these are all approximate. I'm rounding. So then our max type 1 error is 0.025. You guys are probably familiar with that value, but we're doing the one-sided test. So you need to know those other quantiles. They must have indoctrinated me pretty well in those Stat 101 classes that I still remember these critical thresholds. So that's how you compute that. So this is called alpha. And so alpha is referred to as the size of the test. So let me just write down a definition. There's two definitions that they use in the book. I'm going to use size repeatedly until we go through the whole proof of Neyman-Pearson, and I'll tell you why they switched to this notation of level. What they're saying is still true. The size of the test. Is just the maximum in theta is an element of the null set of B theta, and this is going to be equal to alpha. We're going to stick with this. I'm going to replace all of their language about level alpha tests in the Neyman-Pearson proof with size, because it actually is size in that case, but then I'll go back and I'll clarify what they mean about level. So a level alpha test, and you don't need to worry about this. We'll discuss it after we go through Neyman-Pearson. So anytime they use the word level, just replace it with size and you'll be okay in their case. So level alpha test has this property. Max theta is an element of H naught. B theta is less than or equal to alpha, so it's bounded by that. We won't need to worry about that in the way they formulated the Neyman-Pearson lemma, because they're looking at a simple versus simple test and everything is equal to alpha, and it's in their proof case. So it's a little bit superfluous what they say, but there is a small anecdote. It tells us the trade-off in the type 1 and type 2 error. I'll try to be more clear later. So this is alpha. That's what you pick, and that's going to calibrate the maximum of the type 1 error. You'll notice that the type 2 error is going to be 1 minus the power. So 1 minus the power in the alternative set in H alpha is the type 2 error. We've kind of mentioned that before. So this 1 minus the power function is that error that we incur in the alternative space. So here's what Wald, Neyman, and Pearson told us to do. And a lot of people forget to do it. They certainly teach you in a design class. You need to do this. So what they might do is they might say, there's some little value right here, theta naught plus delta, and that's going to be your meaningful effect size. What you're supposed to do is think about that. How far from the null would you need to be before you're willing to reject it? So you could end up computing the power for that value right here. And what a lot of people will do is they'll plug in this value right here when theta is equal to delta plus theta naught. You'll see that theta naughts will cancel over there. I'll still have one over here. I can compute that probability. But what you could do is say, I want that probability to be high. So in this region, I want the type 2 error rate to be low at that point. And so what people will tell you to do is choose N so that you can bring down your type 2 error rate. So we replace this with theta naught plus delta. Same thing over here. Theta naught plus delta. We can compute this probability over here. It's just a z-score. Some z-score, this is still a z over here. And I'm just going to see if my z, my normal 0, 1, usually we call that z right here, is bigger than this value right here. So the k will still be there. I'll have to calibrate to the type 1 error rate, so I might plug in this is what the Bayesians said to do in their ASA write-up. They said, well, stop taking 0.05 as the threshold and take the threshold to be something smaller, 0.01. I don't know what that value is right here, but they would plug that value in here. So if you wanted your type 1 error rate to be 5%, I'll take 1.645 and I'll plug it in right here. So that's a 5% type 1 error rate. So I've calibrated this test, and now I'm going to calibrate it in the alternative space by considering this meaningful effect size. And what we'll do is we'll try to fix that probability. So we'll pick some number. Maybe you want your type 2 error rate at this point right here to be small, so you want the power to be high. And there's only one knob you have to control, and that's N. And so you could solve for N, and a lot of people will have you do that. So what you do is you pick out the critical threshold for the probability to be that value, and you back solve for N. It's a Stat 101 question. So, do they teach you this when you first take statistics and learn about hypothesis testing? A little bit, right? They should. I taught a Stat 101S class in Stat 103, if you must know. A long time ago, it wasn't here, and I spent a lot of time talking about this. I don't know if it like stuck with people. I'm imagining they're just like, what's the correct answer on the test? I don't know what you're talking about. So, but I think it's meaningful, going back to the original question of how far from the null do you really need to be and how do you calibrate that? Neyman and Pearson and Wald said do that for everything. If you can't think of delta, don't do the test. So, and a lot of people fail to do that. What I notice most people do in the literature is that if their p-value is not small enough and they don't reject, then I see people go and abuse this, and they say, well, let's compute the power. It's effect size, and then they'll say, oh, I don't have enough sample size to bring down the power to detect the significance of being in this range right here. So what they'll say is, I need a granting agency to now give me millions of dollars so I can go collect more sample. So they'll end up doing this if their p-value doesn't duck alpha, and then they'll say, I need a bigger N to be able to do this detection. I don't like that. That's not science. This could go on forever. And eventually you'll find an N that ducks alpha, and that's guaranteed with probability 1. So people have turned this into a game, but I think you're supposed to say up front what your thresholds are. You're supposed to say what alpha is up front. You don't speculate after you compute the p-value, and you're supposed to say something about delta. So I'll address this a little bit more when we get into Bayesian testing, that's all buried into the Bayesian posterior probability. Okay, that's what a power curve looks like. That's all in the book, and you can study that. I want to point out something really important about this power curve. This power curve is monotonic, and that means I like it, and everybody likes it. No huge debate. So note, power curve is monotonic. This is important. So remember what the original thing that we're doing is we're computing a test statistic based off of this criterion right here. So that's our likelihood ratio test stat criterion for rejecting. We'll pick C to calibrate the type 1 error rate. C's not K, but it's 1-to-1 with K. And so you tell me what K is, I'll tell you what C is. So not exactly the same things. Notice that this is only makes sense if this thing is monotone. If all of a sudden this went up and down, this wouldn't be a very reasonable criteria right here. Should be getting bigger or smaller as I move in a particular direction. And if you don't have that, then I'm not sure this criterion makes much sense. So I want to point out in the Sharp test, the power function that we end up using is not monotonic. We'll come back to that after we prove the Neyman-Pearson lemma. So some of you might know what they do is they come up with a power curve in the other direction, and then they chop these parts out to make the test unbiased. I'll tell you what that is later. Let me make a statement about Neyman-Pearson and just tell you what it is. So there's other examples that are in the book about rejection regions and computing power curves. I would suggest run through those, look through them. If you're reading through them, just with book in hand and no pen and paper, you won't understand it very well. You have to go through and do the little calculations and verify everything. I'll go through one more example next time, just so we understand what's going on. I'll go through the binomial example, that's in the book, so maybe you can look ahead. But I want to make the statement of what Neyman-Pearson said. So this is the Neyman-Pearson lemma. We'll try to prove this next time. And I don't think Neyman-Pearson sent back stats 200 years. I'm thankful for their clarification on everything. I wish everybody else understood what they said, what they were saying to do instead of turn us all into robots. They weren't saying that. So let me write it down exactly using the notation in the book. They kind of change up the notation on us a little bit. We have to understand what they're saying. So consider testing. H naught, theta is equal to theta naught, and H alpha is theta is equal to some other value. So theta naught and theta 1 are some value. I'm assuming I've got data that was generated from f of x given theta. So I have some data point from it. I'm going to consider it some, this could be a scalar value, it could be something high dimensional. So it could be a vector, it could be a matrix. So, but all that I know is I've got some function, and when I plug x's in and theta's into it, it's a number. So we're going to test this. This is the simple versus simple hypothesis test. I think most people will call it that. I kind of like that name. I don't have any problems with what Neyman-Pearson said in the simple versus simple case. I don't have any problems with what Neyman-Pearson said in the one-sided case. It's just an extension of everything. I do have a problem with, I guess they didn't say it, I do have a problem with using this theorem in the two-sided case or in the sharp test. So, but I think these are totally comparable hypotheses. I think those are totally comparable hypotheses. That makes sense. In the sharp test, I don't think that's really necessarily comparable on its own. You have to make a lot of assumptions. I'll tell you what the assumptions are. So the Neyman-Pearson limit doesn't exactly correspond to the sharp test. Not on its own. Okay, here's what they say. So, one, there's a couple conditions here. X is in the rejection region. If, and they write down a condition for you. This is f of x given theta 1 is going to be greater than, just remember it's the simple versus simple test. It's going to be greater than f of x given theta naught times k, where k is going to be some positive number. Could also be 0. 2, x is not in the rejection region if f of x given theta 1 is less than, I'm going to get rid of that equal sign, k f of x given theta 1. You might ask in this, where did the equal sign go? I'm imagining everything is continuous in this case. They didn't throw away the equal sign because it's continuous and it doesn't matter where you put it. They threw it here on the k. So they let k have the equal sign in there that is going to be in there. So it's superfluous to write it on one or the other. So 1 and 2, these are just conditions. I'm going to say a few things. So, A, the test, oh, and I should say, let me actually write it out. This wasn't the second condition. 2 was going to be the probability that x is in the rejection region and I'll write given theta naught. Remember, I don't have to consider the maximum over the set because there's only one value in the null set. Theta is equal to theta naught. So I don't need to take limits or anything like that because there's only one value in all of this. I'm going to say that's equal to alpha.
Professor, is this
That one's 0. Sorry. Let me just finish writing this out and we'll come back and we'll prove it next time. So, A, if 1 and 2 are true, the test is what we call a UMP. It stands for uniformly most powerful. What that means, a test that's uniformly most powerful, so I'll say UMP theta, so its power function is greater than any other power function. So some other test. So this is the power function for a UMP test. Another test. So any other test that I can find in the same class of tests that has a bigger power function when theta is an element of the alternative space is more powerful. The power is higher, the type 2 error rate is lower because we're looking in the alternative set. So if 1 and 2 are true, the test is uniformly most powerful, size alpha. Here's the kicker. B, if a test is UMP and size alpha, it satisfies 1 and 2. What does she want? So what it's saying is that every UMP test, this is the size alpha part, we're just constraining it to be size alpha. So it's basically referring to 1. The size alpha part is the 2, and this is the condition for things to be uniformly most powerful. And if there is a UMP test out there, it satisfies this. Somebody tell me real quickly, what is this criterion? That is the likelihood ratio test in disguise. So this is the L.R.T. We'll come back next time, explain that that is the likelihood ratio test in disguise. It's just the ratio of these two maximum likelihoods over simple sets. And they've redefined the constant because they inverted that function that we were playing with before. We'll look at that next time and we'll try to prove this statement. We'll look at another example or two. Thanks you guys, sorry for running over.